Hey guys, today we'll be talking about question 5 from the 2021 special exam. As I said before, question 5, I guess the 2021 special exam itself, it was one of the harder ones. A lot of students struggle with this exam from the 2021 year. But today we'll just be going through some of the questions, or question 5 in particular, just talking about some of the problems the students had and how we can, get through them. Okay, just before that, I wanted to point out that in the previous video I went through question 4, um, especially part C and part E from question 4. As you can see here, I just labeled 6% and 3% there. These numbers sort of represent the percentage of students that actually got the full 3 marks of this question. Um, why do I think such a low number got these both correct? I feel like just from my experience as a student, from my own experience as a student, students tend to ignore some of the hints that VCAA gives you. For example, with this question, right? You needed 2 pieces of information from part C to answer this question. One was one was this point, C, which was 16.4. The other one was the fact that the track and the path joined up smoothly, which means the same gradient, right? Without sort of, if you were just to sort of ignore this, you wouldn't have gotten the answer correct. You wouldn't have been able to have enough information to be able to answer this question correctly. Um, but also another point, right? Part A, VCAR does tell you to put it into this form, into Cartesian form. You can still use parametric form to solve questions like this, to solve these problems, but I believe Cartesian form is just much easier. As you can see, it just allows you to, not have to deal with the whole time aspect, because in no point in any of these questions do they ask you about time, which should give you a hint, right? That we don't need to worry about the parametric form. The Cartesian form is just much more convenient to deal with, anyways. Um, but yeah, that's as you can see, as we went through them, you can see that they're not that difficult. Just takes a bit of understanding of some of the key concepts involved in these questions, and I did point out quite a few ideas that you can take away from them. So, anyways, we'll go ahead to question 5 now, and we'll see what we can do about this one. Um, just before we start, what I might do is I might label some of the forces acting in this diagram. So first thing I'll do is I'll label the tension forces. It's good to remember that because we're dealing with a single string, right? Tension forces are always going to be the same in the string, and in this case they'll be equal and opposite, because this tension force is what keeps this mass in place, and the other tension force is what keeps this other mass here in place. Um, next thing I'll do is I'll label the weight forces. So mass times gravity, m2g, where g is equal to 9.8. Here it's going to be m1g, and we know that the weight force acts straight down. So m1g. Um, we also need to worry about this normal force acting on this mass here, because m1's straight on the plane. It's m1 sitting on the plane, so obviously the plane's going to push back onto m1. So we have the normal force acting, which I'll label as n. Okay, so yeah, that's it for now. We'll leave. There are some forces, such as the friction force, that will be introduced later in the question, but we'll leave it for now. Okay. Okay, so given that the inclined plane is smooth, find the relationship between m1 and m2. The mass m1 moves down the plane at a constant speed. So we know that the mass m1 is to move down the plane this way, right? We are moving down the plane, okay, and we're moving down at a constant speed, which means acceleration is 0, right? So we'll just note that acceleration must be equal to 0. Okay, so how do we write, the the equation, the resultant equation from this force diagram? Well, we know our formula is R, which is the resultant force, is equal to ma, right? In this case, what is the resultant force? Well, if I was to just resolve my weight force into its component that's perpendicular to the plane, the component that's horizontal to the plane, I mean, sorry, parallel to the plane, well, the perpendicular component is given by m1g cos theta, and the parallel component is given by m1g sine theta, right? Obviously, the parallel component is the one we're interested in, because the parallel component is the one that, is actually going to move this m1 mass down the plane, which is why I will use which is why I'm resolving the forces parallel to the plane, and I'm going to use this value right here, this m1g sine theta value. right? M1, so therefore M1G sine theta is equal to, oh wait, we have to deal with this M2 mass here. Well, the only other mass that is opposing this M1G sine theta force, the only other force opposing it is this M2G force. So M1G sine theta minus M2G is equal to mass times acceleration. So remember, we're dealing with a full system here, so we have to um, so the mass of the system, the mass that's in this formula, what m refers to in the formula here, is the mass of both of them added together. So m1 plus m2, essentially the mass of the whole system, right? And since acceleration is zero, it doesn't really matter in this case. These both just go away. So I end up with m1g sine theta is equal to m2g. This case, theta is indeed 30 degrees, so I replace this with 30. Then I'm going to get m1g on 2 is equal to m2g. The g's will cancel out. Therefore, I get that if I multiply both sides by 2, I'm going to get m1 is twice the size of m2. Okay, and that's all for now, for this question at least. Let's move on to part B. In part B, we are told that the masses are placed on a rough plane inclined at 30 degrees. So the rough implies that there's friction that's going to be involved. Everything else seems to be the same. We're also told that N is a normal force, just like we did before. Um, yeah, exerted by the mass m1 because m1's on the plane. And the resistant force of magnitude delta n acts on and opposes the motion of the mass m1. Okay, so these are the key parts of this problem here. Okay, so what can we do next? Well, just before we go on to solve part B, I should mention that the concept of friction was actually part of the special study design up until 2016, I believe. Afterwards, it was removed because for some reason, not really sure why it was removed, but it was removed. And now we don't really deal with friction. But these types of questions, these sort of like hidden friction questions, do tend to pop up in a lot of these later VCAA exams. And just knowing how like friction works will give us a good idea on how to like solve problems like this. Well, all we need to know, to be honest, is the formula for friction. So the friction force, that's given by the formula mu n, where mu is called the coefficient of friction and n is the normal force. Okay, so that's how. So the product of mu and n will give us the friction force that will oppose the mass. That will oppose the mass in whichever direction it's moving in. Okay, the coefficient of friction is pretty much this number between 0 and 1 that is with that you're just sort of told, right? VCAA used to just tell you the number. Um, um, VCAA used to just tell you whatever the value of this was. Yeah, so it's just something that it's just like a constant value that you'll be told. But n here is normal force. How do we calculate normal force, right? As I mentioned before that whatever the masses act, I mean the forces acting on m1 is this weight force here, m1g, and the normal force that the plane pushes back on m1 with, right? Well, obviously this mass m1, right? All it does is it sort of moves parallel to the plane, right? It doesn't move upwards, it doesn't move downwards, it just moves parallel to the plane, right? So why doesn't m1 accelerate this way or accelerate this way? Well, because we know these forces are balanced. This normal force here that acts on the mass m1 is balanced by this other force here that I've labeled m1g cosine theta, right? So the reason why the mass doesn't move off the plane or anywhere else is because the normal force n is completely balanced by the other component, by the perpendicular component of the weight force, which is m1g cosine theta. Cool. So that's what we have. Let's go and try part B. So mark and label all the forces acting on the mass on the diagram above. Okay, let's just finish off with our um, let's finish off with the problem here. We've already started most of it. We've already labeled most of it. Um, all we have left is the this friction force. Okay. Um, does it tell us which way it moves? Let's see. Okay. So since we're taking the direction up the plane as positive, since the mass is moving this way up the plane, it only makes sense for the friction force to oppose the motion of the mass. Therefore, the friction force should be acting this way, right? And I'll just label that with what it was called, delta n. Okay, so the friction force is opposing the motion of this mass m1 up the plane. Okay, so let's try and do part two of part B, right? So taking the direction of the plane is positive, find the acceleration of the mass m1 in terms of m1, m2, and delta. Okay, so if you're moving up the plane this time, what forces are influencing this movement? Well, if the mass m1 is to move this way, we know that this m2g is going to be driving that motion, this m2g force. What's going to be opposing it is the weight force of m1 that wants it to go down the plane, and this friction force. Therefore, we can write our, R equals ma equation as m2g, which is the force, pulling m1 up the plane, minus the weight force of m1, which is m1g sine theta, I guess the parallel component of the weight force, right? Minus the friction force that opposes the motion of m1 up the plane. Okay, and that obviously, because we want to find acceleration, again, we're considering a whole system, so we have m1 plus m2 times the acceleration, right? Because we are talking about a whole system, we have to consider the mass of m1 and m2. Okay, cool. What can we do next? Well, we want to find m1, m2. We want to find this the acceleration in terms of m1, m2, and this delta value, right? So we want to get rid of n, but we know what the normal force is, right? We've already calculated it. Normal force, as I mentioned before, it's completely balanced by the perpendicular component of the weight force. So the normal force is m1g cosine theta. So what we'll have next is m2g minus m1g sine theta, which is just 1 on 2. So I'll just write this as m1g on 2 minus delta times m1g cosine of 30 degrees is equal to m1 plus m2 times a. Cool. Let's keep going with this. Well, I guess at this point you can sort of put in your CAS, and you could, you don't have to really like try and, simplify everything, but we can keep going with this anyways. So we get m2g minus m1g on 2 minus delta times g times m1 cosine 30, which is root 3 on 2, is equal to m1 plus m2 times a. Okay, and I guess now we can put it all under the same denominator. They all have a denominator of 2. So if writing everything on this side with the same denominator, I'm going to get 2 times m2g minus m1g minus delta g m1 root 3 all over 2 is equal to m1 plus m2 times a. And this is just going to simplify to a is equal to negative g on 2 times m1 plus m2 times delta m1 root 3 plus m1, sorry, plus m1, I'll write at the bottom maybe, plus m1 minus 2 times m2. Okay, and that's it for this question, for this part of the question. That's what our acceleration is. Okay, so now we'll go on to part C and part D. Again, I've labeled the percentage of students that got these questions correct. 11% got the full 2 marks of part C, and 3% got the full 3 marks of part D. So they are pretty difficult questions, but let's try and go through them together and see whether we're able to understand what's sort of going on here. Um, so part C starts off by saying that sometime after the masses have begun to move, the M2 mass hits the ground at 4.5 meters per second, and the string becomes slack. Okay, so what happens when the string becomes slack? That's the question we sort of have to understand. Like that's sort of what we have to understand when sort of have to imagine in our mind, right? The idea is if we have a plane, right, and we have a mass and it's being pulled up this plane, right? Imagine this M2 mass now is on the ground, right? It's on the ground. It's not moving anymore, right? This string now doesn't have tension anymore. There's no more tension force. There is no tension force in the string because the string is slack, right? There's nothing. There's no longer a force pulling the string, pulling this mass up the plane, right? Hence, there's no force really that's pulling this mass up the plane. So this mass is sort of stuck there, right? So that's what sort of happens when the string becomes slack, right? This is so that at this point, we're told that M1 is at the point P on the plane, right? So I'll just label this as point P, okay? Which is 2 meters from the pulley, right? So we know from P to the pulley, that's 2 meters. Okay, and here, there we go. We've got our coefficient of friction, which is 0.1. So what we want to find in part C is how far from point P does the mass M1 travel before it starts to slide back down the plane. Okay, so we want to give our answer in meters to two decimal places. So again, what we have to do first is we have to find acceleration. The reason why we can't use acceleration, the value for acceleration that we got from the previous question, is because this scenario is now different, right? This M2 mass, right? This M2 mass is no longer pulling this M1 mass up the plane, right? The string is now slack, right? Whatever it's making, so what this means is the M1 mass still has its own velocity. It still has its own velocity, which means it's still traveling up the plane until it's being slowed down enough by the friction force for it to go back down the plane. Because obviously, the friction force is still acting. So we still have this friction force delta n that, opposes the movement of M1, right? But from its initial movement, right? From the initial movement, M1 still has a velocity up the plane. Because M1 still has a velocity up the plane, right? It doesn't make sense, does it? For as soon as M2 stops moving, for M1 to also stop moving, right? Because there's nothing for that, there's nothing that will immediately make M1 stop moving. So that means that M1 still has a velocity up the plane. Sort of think about it as, pulling something behind you, pulling like tying a string to something and pulling it behind you. And imagine you're running, right? If you stop running, does that mean the object behind you is going to stop as well? No, because you're pulling with the string. The object behind you has a velocity, which is why M1 still has this initial velocity of the plane, which is why it will still travel up the plane before it eventually begins to slide down. Okay, so again, let's label all the forces acting on M1. In this case, there is no more tension force, so right now we just have this friction force acting on M1, and I guess also this weight force, right? We still have M1G, and we still have its parallel and perpendicular components acting on it. So now we want to find how far from point P does the mass M1 travel before it starts to slide down, or slide back down the plane. What can we do here? Well, let's find the acceleration first. Okay, so let's just resolve all the forces. Um, Now this force is pulling it down the plane. This M1G sine theta is pulling it down the plane, so I'm going to write it as negative M1G sine 30, right? Because remember, that's the parallel component of it. And if you didn't know, it's because this triangle there, the reason why it's also M1G sine 30 is because the reason why both angles are 30 degrees is because these triangles here, this triangle, the force triangle in here and the triangle down there, and like I guess this whole ramp here, they're both similar triangles, which is why this angle here is also 30 degrees. But anyways, yeah, so this force is pulling it down the plane. The friction force is also forcing it down the plane. The friction force, which is delta n, which I guess I'm just gonna now write as 0 0.1. So delta is now 0.1, and n is m1g cos 30, right? And that's equal to mass times acceleration, right? Now at this point, we don't have to write m1 plus m2 again because m2 is no longer involved in the system. M2 is now hit the ground. All the forces acting are just on M1, right? All the forces that influence M1 move this mass's movement is purely from the mass itself, right? The friction force, its weight, and its weight force. Okay, so just M1 times A. What we can do is we can sort of go ahead and just simplify everything. This just becomes minus M1G sine 30 is 1 on 2, so M1G on 2 minus um, 0.1, we can just write that as 1 on 10 minus 10 cos 30 is going to be root 3 on 2, so root 3 on 2, and then we just have this m1g there, m1g, right? So m1g times root 3 on 10 times 2, which is 20. That's equal to a. Just simplifying everything, once you simplify everything, you're going to end up with this value. A is equal to negative g on 20 times 10 plus root 3. So you'll notice there's a negative value, and that makes sense, right? Because now the only forces for working on M1 are forces that push it down the plane, right? Hence why, if M1's direction is, if we consider going up the plane to be a positive direction, then the acceleration and the forces are forcing the mass to go back down the plane, which is why acceleration is negative. Yeah, but anyway, that's our value for acceleration. What can we do now? We can use one of the constant acceleration formulas because obviously this value here is a constant value. We can use a constant acceleration formula in order to find how far up the plane it's gonna start traveling, right? So remember, point P is defined as the point where M2 hits the ground. So we want to find like how much further than point P is M1 going to start traveling up the plane. Okay, so let's go ahead and try doing that. Um, so the formula is v squared is equal to u squared plus 2as, right? Um, at point P, we're told that M2 hits the ground at 4.5 meters per second. Okay, so that's a key value. That also happens to be the velocity of M1 at that point P. The reason why is at the moment M2 hits the ground, right? They stopped acting as a full system. But I guess the instant before that, which is where M2 hits the ground at 4.5 meters per second, that's the value the whole system was moving at, right? That's sort of the speed the whole system was moving at until M2 suddenly stopped moving, right? So M1 starts off, so because the whole system is moving at 4.5 meters per second, um, yeah, so because the whole system was moving at that speed, M2 stops at that speed. M2 stops at that speed, and M1, will continue at that speed until it's been slowed down by this friction force. So we know our initial velocity. Our initial velocity is 4.5 meters per second. So remember, this whole equation here is just dedicated to M1. So initial velocity is 4.5 meters per second. What else do we know? Well, we know our acceleration, obviously. We also do know our final velocity. And think about why we do know this, right? M1 is going to continue up the plane until it can no longer move, right? So it's going to keep, so imagine what's happening right now, right? M1 has a certain velocity, which is 4.5. So it's starting with this 4.5 meters per second, okay? But it's being resisted by this, it's being resisted by these two forces, which is, m1g sine 30, which is the weight force pulling it down the plane, and it's also being resisted by this, friction force, which is delta n, right? So these two forces are pulling it down, right? So at a certain point, so what's happening is as this mass travels up the plane, these two forces are progressively lowering the speed until the speed turns to zero, right? At the point where the speed turns to zero, afterwards it's going to start falling down the plane. So eventually this number here, 4.5, is going to get smaller and smaller and smaller until these two forces have completely reduced the speed to zero, and this mass now goes down the plane. So it's going to go up by a little bit more until the speed goes to zero and the mass just starts going back down the plane. Because remember, there's no other force pulling out the plane, right? The only reason why M1 is still going out the plane is because it still has this initial velocity, which means it's still going up the plane, right? The only reason why it's still going up is because it still has this initial velocity, which it started with. But eventually that velocity is going to go down to 0. So our final velocity is now 0, so 0 squared is equal to 4.5 squared plus 2 times a, which is now minus g on 20, 10 plus root 3, 2a times s. And we can just put this in the cas and solve for s. S in this case, once you round up, I guess once you round to the nearest, to do decimal places, you're going to end up with 1.76 meters. And that's our answer for part C. Part D now becomes a little bit harder, okay? Because there are a few other things we have to worry about. So it says, find the time taken from when the string becomes slack for the mass m1 to return to point P, okay? So again, let's just sort of think about what's happening here. If I draw the diagram for you again, right? And I'll just sort of model the motion of m1. So we have the point P here, right? m1 starts at point P, right? When it reaches point P, obviously m2 has already hit the ground, right? M2 has already hit the ground. It's no longer sort of involved in the motion anymore. It's no longer pulling m1 or influencing the movement of m1 in any way, right? So m1 is going to go up by a little bit. It's going to go up by a little bit, right? And then, as I mentioned before, these two forces are going to start pulling it back down. So once this velocity, 4.5 meters per second, once that's been reduced to 0, this mass m1, so it's going to go up here a little bit, so it's going to go up there a little bit, and then I'm going to just label this as like maybe t1, right? So after t1, it'll be, a little bit beyond point P, and then at point t2, that's when this mass is going to fall all the way down back to point B, right? So T2 is when, it sort of arrives back at point P. So that's what's happening right now. And what we want to do is we want to find what T1 plus T2 is. Okay, so that's what we want to find. We want to find the total time. Okay. So we can find what T1 is. We already know what that is, right? We already know we can use this acceleration from the previous question. In this case, we want to find time, so we can't use this formula anymore. The formula we can use is actually s is equal to ut plus half at squared. Obviously, because we want to find time, and we know what the distance is, we know what the initial velocity is, and we know what the acceleration is. Okay, so let's go ahead and try solving that. The displacement. So how far did it travel up the plane? Well, the displacement was this number up here, 1.76. But what we need to do is we need to also account for the fact that this 1.76 has been rounded. So don't use just the number 1.76. Use whatever you solved it. Use whatever came after it as well on the CAS that you would have found, right? So sub in. So in this case, it would have been like looked like something like 1.76. 1, 2, 6, 6, 2, 6, 4, blah, 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 right? So use whatever number that you got in the CAS, copy and paste it and put it in. So don't just round it and put it into the next part, because then, you might end up with an answer that sort of differs a little bit when you round it to the nearest tenth of a second. So you want to just avoid any rounding errors. So anyways, you have this number here. Again, so subbing everything in, ut, our initial velocity was 4.5 times t plus half a. What's a in this case? A is this g on 20 minus g on 20, 10 plus root 3. Or maybe I'll just write it down here for you actually. So 1.76, 1.266, is equal to 4.5 t plus half times minus g on 20 times 10 plus root 3 times t squared, right? And remember what this t is. This t is referring to the time taken for this mass to go up the plane, right? So for it to go to this first point here, t1, for this mass m1 to go up to this first point here, t1, right? So maybe it's better for us to label this t as t1. Okay, we'll leave it for now. We won't solve it. We'll solve everything at the end. next thing we have to do is we want to find this t2 time, right? So we want to find, after that, it's going to go back to t2, right? It's going to go back, and after it reaches t1, a certain amount of time is going to pass, which is t2, right? For it to go back to this point p. Okay. Again, we'll be using this formula here, but we have to use another acceleration equation because once the mass reaches t1, or I guess the point out the plane where it stops moving and starts going back down, right? At that point, the motion of the mass is moving down the plane, m1 is moving down the plane. So friction no longer acts down this way, right? Friction is going to oppose the movement of the mass m1, so it's going to oppose it this way, right? So we can't use this equation here because this equation here assumes that friction is going to be, acting down the plane. But now, since m1 is going down the plane, friction is acting up the plane. Therefore, um, this acceleration equation here needs to be tweaked a little bit. So instead of minus m1g sine 30 minus that, I'm going to get minus m1g sine 30 plus 0.1 mg cos 30 is equal to m1a, right? Because now imagine what's happening to the mass. As the mass falls back to point P, right? All the forces pulling it down are pulling it this way. But since the mass is moving in this direction, the friction force is pulling it back this way, which is why it's being, which is why I've changed the sign on it. And again, the reason why this is negative and that is positive is because I've defined going up the plane as positive. Hence why this is plus and that's minus, but that's not too important for now. Anyways, we will end up solving this, and this value for a will be a bit different. A will now be g on 20 times root 3 minus 10. So it's just a bit different this time, but yeah, that's our new acceleration value. Anyways, let's go ahead and solve for t2 now. So I'm gonna write my equation for t2 as minus 1.7612662664 is equal to 0 plus half times a 20 root 3 minus 10 times t squared. Okay, let me just explain why I have, these values as they are. Why do I have a negative sign here? Why do I have 0 here? Okay, the reason for a negative sign is because what's happening here is my mass is from the point where it goes from t1 to t2. So when it's up the plane and starts moving back to point P, right? It's moving in a negative. So because I've defined going up the plane is positive, it's moving in a negative direction. Hence why my displacement is a negative value. Okay, so that's why I have the negative sign there. That's reason number one. Why do I have a 0 there? It's because you look at the formula, S is equal to ut plus half at squared, right? Remember I said I'm moving from when I'm just up the plane here to back down to t2, right? When I'm just up the plane at that point, right? That's when my velocity is 0. That's when I can't go up the plane anymore. Hence why my initial velocity, I'm labeling that as 0, right? And then my acceleration is the same. So half a, or I guess I'm using the new value for acceleration I have, the new one I found, which is g on 20 times root 3 minus 10 times t2 squared. So that's what we have there. Put that in the CAS and we solve both of them now. So once I solve t1 and t2, t1 is going to equal 0.9324 6, something like that. And T2 is going to equal 0.782785, something like that. And then adding them all together, I'm going to get adding them all together and then rounding them off to one decimal place because I want to get the nearest 10 to the second. I'm going to get a total time of 1.7 seconds. So it's a total time of 1.7 seconds for the mass m2 to hit the ground, right? So what's happening here is m2 hits the ground, m1 keeps moving up the plane. It keeps moving up the plane until it hits a point where it can't move up the plane anymore because obviously its velocity is now 0. And then once its velocity is 0, because it still has these two forces, or I guess this force m1g sine 30, its weight force, since it still has its weight force pulling it down the plane, Once m1 is at that point, it starts moving back down the plane, right? Because it can't move up the plane anymore because there's no more forces pulling it out the plane, right? So it goes from this point P, goes to T1 until its velocity, it can't go up anymore. Its velocity is 0 now. Then it starts going down all the way back down to point P, right? And that total time is equal to 1.7 seconds. Okay, that's about it for now. Just let me know if you do have any questions about this, or I guess this question in class, about this problem in class, and I'll be happy to answer it. But otherwise, hope this was clear, and I'll see you guys in the next video.